All right, do we have it? So let's say I draw another box. All right, we have a box. We're going to put 3 gases in it. Let's say we have helium, we have oxygen, and we have neon. All right, what creates the pressure inside the box? All right, the particles bouncing off the walls. All right, so when helium hits the wall, it creates pressure. When neon hits the wall, it creates pressure. When oxygen hits the wall, it creates pressure. All right, what else do they do to create pressure besides hitting the wall? They hit each other, okay? So oxygen hits neon, it hits helium, helium hits oxygen, neon hits oxygen, and so forth and so on, okay? Now, when they do those things, they create pressure. So what Dalton is saying is each of those gases creates what's called a partial pressure. So neon has a partial pressure, oxygen has a partial pressure, and helium has a partial pressure. When you add those 3 partial pressures together, you get the what? You get the total pressure of all of the gases inside of the container. Does that make sense? All right. So the formula that he created to go with that is this. All right. P with a T on it, and that's a T. PT stands for total pressure. The P with the 1, the 2, and the 3, these stand for partial pressures. And I would imagine in math class, you've seen formulas like this that have a plus with a dot behind it. That just means that that formula continues for the number of those variables you have. So in this particular case, I only had 3 gases, so we'd stop at P3. But if I had 5 gases, we would keep going up to P what? P5 and stop. If I had 2 gases, we'd have stopped at P2. But this formula is flexible based on the number of gases or variables you have. Now, Dalton, like the combined gas law, are on the reference table. All right, does everybody have it? All right, so a typical sample that you might see for this would look like this question. Yeah, and if it doesn't tell you what unit, you can choose. In this case, I have it specified, so I'll let y'all choose the unit. A lot of you are going to gravitate towards atmospheres because tomorrow when we do the ideal gas law has to be in atmospheres. And so a lot of you will just naturally gravitate that way after I teach that law tomorrow. But I don't care which one you pick. They're all the same to me. All right, so when you look at it, it's exactly as Devontae said. You want to find total pressure. So what are you going to do? Okay? So if you were listening to him, he said we're going to add them all together. So total pressure is equal to the pressure of neon. This is board taking so long to catch up. Pressure of hydrogen plus the pressure of, what's my other gas? Nitrogen. So he said we were going to add the 2.5 ATMs plus the 653 torr plus the 152.3 kPa. And as Devontae pointed out, they all have to be in the same unit. If you were listening to what I said, did the question tell you what unit it has to be in? Did it say find the pressure in atmospheres? Find the pressure in torr? Sometimes I will specify that in the question. If I don't, you may choose the unit you like best. Which one do you like best, Alex? Choose. Okay, Alex is choosing atmospheres. So that tells us we're going to leave this one in atmospheres, and the other two have to be changed. Now, you can choose to show me the work or choose not to. I will tell you now it's a standard deduction. I don't care if you show me the work or not. If it's wrong, it's -5 for each. Okay? So whether you show it to me tomorrow or not, it's just -5. So 653 torr. Torr to ATM. What goes beside ATM? Beside torr. If you still don't know how to do that, you might want to figure that out by tomorrow. 0.859. Okay? 0.859 torr. Sorry, atmospheres. Goes under the torr. All right, and then 152.3 kPa. kPa. Atmospheres. What goes beside ATM? Goes beside kPa.
101.35.
Okay? That's going to be 1.5. The 1.5 goes below that one.
Do we have to show that?
What?
Like, rewrite it to torr and kPa?
Nah.
Just do the new.
No, the new units are fine. I'm just merely showing where the work comes from. So the total pressure is 4.85 atmospheres. You never know. Angel might get gung-ho and actually watch the video, catch up. This way he knows where it came from. All right, questions about either? How we did either conversion or how we got the answer? Feel okay about it? Yeah? All right, we're not doing that. Now, if you had to find a partial pressure and they gave you a total pressure, would everybody be okay with adding and then subtracting to get the partial pressure? Okay. What? You sure?
I think so.
So if you had, let's say, you were solving for P3, you'd add P1 and P2 together and subtract it from the total to find the P3.
Okay, so
Yeah.
okay, so this P equals 4.85. Is that the same pressure that we use?
Say what now? Hold on, I didn't hear what you said.
I think. Oh, thank you. Okay. So like this, they give us all the pressures.
Yes.
Okay.
So if they were going to alter this, you had to find a partial pressure, let's say for nitrogen, for this last one, they would have given you the total pressure, and you would not know the partial pressure of nitrogen. So this would be like missing, and you would have like P here, and you would know this, and you would know, let's just make up a number, and let's just say it's 5 atmospheres. Okay? So you would add these two together so you could subtract it from 5. Would that make sense? To solve for the partial pressure of nitrogen then?
Okay, now
Okay.
So you like to put things to. So,
On occasion.
like, is there gonna be times when like we have the 2 different units and 1 different like?
Maybe.
Okay. So
You just have to convert.
in that situation, is it best that we change everything to the left of the equal sign to whatever it is out of the equal sign?
I would make them all match. So you could choose. I mean, if this was an atmospheres on this side, I'd certainly make all these atmospheres yes.
Okay.
Yes. Yes. Okay. All right, we're going to practice for a short while. Some of you will move along nicely and finish quickly. Some of you will get bogged down and not get very far, okay? And we'll have to finish homework. I'm just being honest. Because I'm not giving you the rest of the class period anymore.
That's on the back.
I'm going to tell you which ones I want you to do. We're not doing every one of these. I'm going to tell you which ones we're doing.
Yeah. Right. They couldn't have.
And they tried to find something so long.
Who? Yeah. The chief.
And the name is misleading because you get there, you think it's like this nice academy.
Yeah, that's what I think.
But you get there and you look.
What is it sound?
I can't even say it, it's just dangerous.
So it's not like a rich business school. Males are retired. What can they love?
I guess those means that, once I say that, they love that. And that was another big ones, like, didn't have this, like, everything says that they would be, and then all kind of little ones, and like, there's a big section, and the game they got to.
Is this for me, like, with the P one?
This is everything.
Oh, okay.
Now, it's 9:05. We will have stopped by 9:30. Okay? Now, if you can do those, and you can do them easily and well, I would think your chances of making a high grade tomorrow would be stellar. Okay? I would think. We will stop at 9:30 and move on. Here are the answers so that hopefully someone will be asking me a question and you can check your work to see if you have the right answer, because I will be so busy answering someone else's question, you'll need to check your work. Is what?
So you said something about if they don't mention temperature.
Then it's constant. Okay, if it's not brought up at all, assume that it's constant.
So what were you saying that like if it is brought up, and then the temperature is it's brought up?
If it's in the question and they give you a temperature, it's not constant. But if they say temperature is constant or it's not there at all, assume that it's constant. That's it. There's 13 zeros here. Have a question yet? It's time to get started.
You said the answers were up there?
You got it right, Devontae? Ops? Bring it here. Any question, how to work? We're just putting in a couple grades for this afternoon, and y'all fill my homework. All right, what are we doing? Alright. This is all set up right. The formula is there. So you did 455 times, you did these two together. Instead of these two together. Okay? So you just plug it in. So you have 455, that's to say V1 times 99.3. Okay? And then your P2, whatever that is there, it looks like you got P2, has to stay with the 206. You just put the wrong numbers in the wrong places. All right, just pay attention to putting the right numbers in the right places. Okay, take your worksheet. Go. All right, what you got? That's because it's, you don't understand. That's, that worksheet, if I told you how old that is, you'd be appalled. It's right. But when I retyped it, I didn't do centimeters cubed, I did milliliters because it was easier to type. But that's an original from the first year I taught.
This sheet?
Yeah, that's why the paper's so yellowed. It's 28 years old. All right, who else has homework or has a question?
This law,
Yeah.
what is on the volume and temperature in the question, is the formula V1 over T1 equals V2 over T2?
You have volume and temperature on it?
Yes.
It just says, okay, this one.
Yeah.
On the blue sheet, it just for KP it has 101.3. But we didn't need to bother putting the 2.5.
You don't have to.
We don't have to memorize it, right?
You don't have to. Where? Yep. You do. Change the formula. The formula is V1, T1 equals T2, T2. And you wrote that. You changed the formula. So fix the formula. Yes.
It's like.
What did we write down yesterday, standard temperature, remember?
No.
273. So when you read this, and it says this at standard temperature, as soon as you read the word standard temperature, T1 that goes with that is 273 Kelvin.
Okay.
So you're finding the V, which is your question mark, at 19. Okay? Mm-hmm. Centimeters cube problem? Yeah, that's because it's old. When I handwrote it, I didn't mind writing centimeters cube, but when I typed it, I changed it to milliliters. Same difference. Okay, yep.
Sorry.
Yeah, why don't you just kick over? Okay.
Miss Walt, can you explain number 5 to me? I didn't do it right
Right
there.
here. It don't look like it, don't look it. No, that's why. See how it says calculate the volume of a gas at STP? Your question mark volume has to be at STP. That 502 has to be at 29.7 and 96. So wherever your 29.7 and your 96 is, has to stay with that 502.
Okay, question mark here.
Yeah, it can't be there with you. See that question mark? it's still the 96 and the 29.7. That's what I'm trying to tell you. Question mark should be with the 96 and the 29.7. Read the question. 502 milliliters of gas is collected at 29.7. That 502 is at 29.7. So your 502 here has to be here. What is the volume at STP? The question mark has to be with 1 ATM and 273. You messed up your possession. Who else has a question?
Did you have a formula that's P1 over T1 and then P2 over T2?
Yeah. Yeah, I tried to pick something that used all the formulas we've done. Somewhere in the sampling of questions. Yes. All right, you usually can find gas law. See how you've got volume, temperature, and pressure label? Those all go together. And it says calculate the volume, so that's volume at STP. Is the other temperature and pressure. So make this one 1, 1. Make that one 2, 2, and 2. Does that make sense? Calculate the volume. So you're going to volume. Now you will have some that don't match. So you're going to have to make a match. Sure. Okay. You need to pour the juice out at the bottom and slosh it around to get some to sticky up.
This one.
Yeah,
On 9, it says raise the volume occupied by 10.0 deciliters cubed.
Yeah.
Why is it asking for the volume if that's what?
Is there another volume there? Wouldn't you be finding another volume? I gave you a volume.
Wait, the first one is standard temperature and pressure, and then it says the next one's standard temperature, so we have to do temperature at all.
You can leave it out, or you can put it in. It'll just wind up canceling each other out. Because they're each practical, because like the way the wording of the question is, you did what most people do. You have a question to calculate the volume at STP. Wherever you put your question for volume, instead of STP. Okay, so when you look at what you did, so you put the 502 with the STP, the 502 says 502 at 917. So this 502
Oh, wait.
has to be
Of course, he gets in there. Oh, right
question
there.
mark needs to be there. Just flip those.
On this one, it says, what is the volume, but then it gives a volume. That's not what it says. What is going on by gas and standard pressure?
So this volume has to be at 1 atm.
Did that,
Okay, so then you're finding the volume at that level.
but why does it say first?
Doesn't matter, it's just the way that,
Well, that's what messed me up over here.
well, I'm telling you, this volume has to stay at, it says at, those two have to stay together. You're finding the volume, it goes to that 500 kPa.
Yeah.
So in about 4 more minutes, who else wants to ask me questions? Right, see how it says calculate the volume at STP? You find the volume at STP, so there's your temperature and pressure. So I would make that one P1, P1, and P1. If the volume is collected at the temperature and pressure. So I would make that volume 2, that pressure 2, that 502 is collected at that temperature and pressure. The 502 has to stay with those two. Okay? Okay. Okay, there's so- Did you change that? Or did you leave it in Celsius? Okay, I was gonna say, 'cause looking at that, I didn't see anything more glaringly wrong, but I don't think you changed it.
Look down there.
At a quick glance, you change the formula. Formula is D1P1 equals D2P2, and it looks like you changed it to D1P1 divided by D1. It looks like you wrote it P1 over D1 equals P2 over D2 is the way it looks like you wrote it. That's what it looks like, which is wrong. You need to plug it into that. Okay? All right, I can tell you that part is correct. Plugging it in is correct, but your math is wrong.
The works right here. Shut my way off, bro.
Okay, that's right.
Still. Oh. No, don't look at
Give me
it.
my calculator over there. You work that. You gonna take your second? How much? This is working. Okay. Cause you work right. Yeah, good. Yeah.
You were able to go for it.
All right, here it says, calculate the volume of the gas at STP. So calculate the volume at STP. That's T1,
Okay.
P1. Okay, see how it says, if the volume is at 29.96, so that is volume, and that's temperature, and that's pressure, right? And that 502 is collected at that temperature and that pressure. So this volume has to stay with those two. Okay? Remember which volume is that?
I did.
Yeah, what the?
You want me the first?
Oh my god.
Okay.
Just send me.
She changed the formula. She did like the V1. That's the thing. Yeah, she changed it.
No.
She changed it to what? She didn't change
Thank.
For our consider genius.
Oh, okay.
Oh, you gotta turn another page. It'll be on the white page over there.
I did.
all those units on it. 14, what is the partial pressure? 2.62 atmospheres, 265.4 kPa. This, any of these three answers are correct.
Wait, it says climate total pressure.
Yeah, those are total pressures.
You said that the total pressure was everything combined.
Yeah, this. I just did it 3 different units
Oh.
because I didn't tell you which unit to do it in. So I gave it to you in all 3 units because I didn't know what unit y'all were gonna do it. So you got 2.5, I got 2.6. It's probably close enough. So I got 0.6, you got 0.57, 1.35. That's off a little bit from what I had, but it's probably okay. I don't see any big deal.
You don't go.
Welcome.
I know about anyway. You just said it. Yeah.
All right, I have 9:35, so I gave you more time than I planned to. So let's move on. If you have not finished and would like to finish, then consider that homework. Okay? I will not be checking it. It is strictly for you to do well on the quiz tomorrow. Okay? You will see one of each question on the gas laws that we have covered thus far tomorrow on the quiz. Each of the questions is worth 20 points.
Can I see the, yeah, can I see one? You see that, right?
Yep, hurry up.
Can I take a picture so I can see if I got it right when I'm doing that?
Yep.
Hey, where's 14? Oh, okay. Is this it?
14 is there, and I put 3 answers because I didn't know what unit y'all would do it in. Oh, make it quick. Come on.
Wait, I couldn't see something. Wait, where's the answer?
You can't see the
Oh,
red. It's like a.
Because it's in the
Here, hold on, let me see.
page vectors.
Okay, got it.
Just holding a piece of paper over a hill. All right, we're going to talk about Avogadro's principle, and then we're going to move on to the ideal gas law. We won't get very far with the ideal gas law, but we can do. All right, I don't know if this is Almira or Jada. I don't know who y'all comes. I'm not sure we can even blame it on not being able to see today. Now, Avogadro is the same Avogadro we talked about way back at the beginning of the year. Okay? Avogadro's principle states that equal volumes of gases at the same temperature and pressure will have equal numbers of molecules. So, for the rest of the week, we will be using mass and moles. So far, for the first 5 gas laws, I have stayed away from everything that involved mass and moles. I'm not going to do that for the remainder of the week. By Friday, we will be bringing back balanced equations. So try not to freak out for some of us. All right, today and well, tomorrow especially, and what's tomorrow? Wednesday, tomorrow, and the first part of Thursday will be pretty easy. All right, the latter part of Thursday and Friday is where we bring back our balanced equations, and we will test early next week. Now, Avogadro's principle states that equal volumes of gases at the same temperature and pressure have equal numbers of molecules. So, if we have two containers, okay, and let's just say that we know that they have the same temperature and pressure, okay? We know their temperature and pressure is the same. We don't know what it is. We just know it's the same. We know their volume, let's just say for the sake of argument, is 1 liter on both of these containers. Okay? That's what Avogadro is telling us. We know the volumes are the same, and we know that they have the same temperature and pressure, whatever it happens to be. He's telling us we can assume what about the inside of the gas container? That's right. The number of molecules is equal. Okay? Now, do we necessarily know what that number is? No. We just know they're equal. But we don't necessarily know what that number happens to be. It's just an equal number. Now, he went further than just that, though. I'm still waiting on people to catch up. Am I giving everybody enough time now? All right. He went a little further, because Avogadro is special. So, suppose he takes a container and he puts 1 mole inside. Okay? And he does it at STP. All right, first of all, if he does it at STP, based on what we were just practicing a while ago, in case there's a few people who didn't get that far on the worksheet, what does STP stand for again? So what special numbers do we know from STP? Okay, so 273 Kelvin and 1 atmosphere. Okay, so he provided those conditions. So if he knew there was 1 mole in the container, all right, if he had another container and he also put 1 mole in it, all right, and he works backwards this time. He says, I have equal numbers of molecules. All right, if he works backwards, what can he assume about the volumes? Okay. He will also have equal volumes. Yes. Now, again, this only works if what? The temperature and pressure is what? The same. It has to stay the same. Now, in this particular case, he gave us STP. So, not only are the volumes equal, he determined the volume. Told you, because he's extra special. Okay? Now, the volume is 22.4 liters. This has a name. This is called standard molar volume. 22.4 liters equals 1 mole if you're at STP. Now, that's all well and good, but how often are we going to have exactly 1 mole? Very rarely. Now, we could often be at STP, but we're rarely going to be at 1 mole. So that's sort of a special case that Avogadro figured out. So we want to be able to apply Avogadro's in some problems. So we're going to look at a problem. All right, does everybody have it written down? Tell me when you got it, Diamond. That way I don't just ask repeatedly. While I'm thinking about it, remember, I'll be here this afternoon if anybody wants to do test corrections. Okay. All right, I'll give you a minute to write that down. And then we'll talk about how you know that's Avogadro. Got it? Or do I need to be still?
Still.
Okay. All right, how about now? Have been still long enough? All right, tell me what's different about this one than the ones we've just worked. Because remember, these are all going to be mixed up on the test. And some of you are going to be looking at them like, all right, it says molecules. That's one thing that should jump out at you. Okay? It has the word molecules in it. So that should be a definite clue. What else is odd compared to what you just worked? All right, you worked some that had leaders, so that shouldn't look odd. You worked one about 5 of you worked one last night that had scientific notation. You know, because I did give 13 zeros today for homework. So not a lot of you did one that had scientific notation last night. But practice problem number 3 had scientific notation. You may see some on the test that have scientific notation. So that should not be a clue that something's weird.
There's different gases, but that's the same.
Dalton's law had different gases. All right. It says temperature and pressure remain the same. And the ones we worked earlier, how many of them remain the same? 1. Temperature remains the same. So you could have picked P1, V1 equals P2, V2. If it said pressure remained the same, you did V1 over T1 equals V2 over T2. But did we have any where both remain the same? No, you don't have any formulas where both of those remain the same. What formula are you going to pick if 2 of them are the same? Okay, so we got V1 equals V2. That's all we got. Okay, that's a really short formula. All right, so when both of them are constant, there's no formula when 2 constants. Okay? There's no formula when there's 2 constants. That's the first thing we should notice. All right? We also notice there's molecules. So, when there's 2 constants, this should tell us that we're Avogadro's principle. Okay? Now, what can you tell me about the volumes? Okay. So the volumes are same. So what does that tell you about the molecules? Okay. The molecules must be the same. So what's the answer? 5.23 times 10 to the 25th molecules. That's it. You just got to read. All right. Now, to quote Diamond from earlier, sometimes Ms. Wall tries to be tricky. Okay? So let's say that I try to be tricky. Okay? I might. You never know.
Isn't the test already made?
It is already made.
Yes.
All right. So let's just say that I try to be tricky. I might not.
You know.
Okay? Well, I'm not going to tell you if I am or am not going to be tricky. What would be the fun in that?
You should try and see.
So let's just say that I try to be tricky. Okay? And I write the question just like this, but I do that to the volumes. How would that alter the question? If I double the molecules, or excuse me, if I double the volumes, would that do anything to the molecules?
No, you can't do it. You have to double them.
You'd have to double the molecules.
Okay, well, what if it's some weird, like, 2.5 difference between the 2?
Why would I do that to you? I'm not that hateful.
Well, obviously you are. You're getting on the first one.
Well, if I made it 2.5, what would I have done to the volume?
Okay, not have to. That's not what I mean.
If I have to, what would we do to the molecules? You would have to.
That's not the point. Like, if it's like.
I was trying to be nice and only double it, but if you want to half them, I guess I could half them.
No, I'm sorry.
You had to change it.
Okay, we could certainly do that. I don't think that's out of the realm. Okay. Now, does everyone